Hello everyone, we are group number 1 in the Mech 491 design project. Our project is about design and analysis of viscoelastic compaction modeling for materials. Coordinator of the lecture is Professor Çağatay Başdoğan and our main supervisor is Professor Murat Sözer. Since me and my partner do not have a picture together, we used the one from our teaser video as you can see. Team members are Cihan, Turgut and Ahmet, Kadir, Zeybek. We both are senior mechanical engineering students. First of all, viscoelasticity is an important aspect of material selection, and this is why this topic is an important issue to discuss. While analyzing this feature of materials, we try to integrate the real-life parameters into virtual models like Maxwell, Kelvin-Voigt, linear standard solid, Burgers, and generalized Maxwell model. And also we compared them with each other. In this project, our goals were doing literature reviews about materials and different viscoelasticity models, using the parameters from articles and creating simulations through Abacus, curve fitting in MATLAB from the Abacus data, comparing the MATLAB results with given parameters, and lastly calculating the error percentages. As you can see, here are parameters of a type of concrete. The Young modulus is 11.975 gigapascal. Poisson ratio is 0.1866. Shear moduli and bulk moduli are 0.999. The strain is 0.1 and tau, which is relaxation time, is 18.242 seconds.
For the abacus part, we define and modelize our material with a constant strain of 0.1. This simulation goes for 150 seconds as the constant given as a step input at t equals 1 and set time is 1. Here you can see from the model that our element has only consisted for the strain in one dimension. Other parts are fixed to obtain a clear result. After the simulation, we take the stress time values from the center of the material and noted the data for the MATLAB implementation. This simulation helps us as a real-life experiment as we can compare our models based on simulation parameters and results. For the MATLAB part, Maxwell, linear standard solid and generalized Maxwell diagram has been used. As Kelvin-Voigt and Burgers models gives inaccurate representation for the constant strain situation, we choose not to use them for the modeling part. In MATLAB, we wrote the general equations of the model and curve fitting is done for the unknown parameters. As from the graphs, you can see that all fitting has been done with 95% confidence interval and ideal parameters has been seen. After going in the process with all models, we found the spring elasticity and relaxation time tau from the curve fitting. Also, generalized Maxwell diagram has been done with both 2-arm and 3-arm modification to comparison between parameter values. In the result, we compare the R-square error results and analytic tau values to obtain a conclusion. With the 0.9918 R-square estimation and 1.174079 error rate, generalized Maxwell model with 2 arms gives us the best accuracy for the representation of the model.
As a conclusion, generalized Maxwell model has a greater accuracy than the other models like Maxwell, linear solid, etc. And also 2-arm generalized Maxwell model gives more accurate results with the relaxation data than 3-arm generalized Maxwell model. The reason behind this is that the model of 2-arm represents this material better because models' accuracy can change with the specifications of the material. With the data from this experiment, we can conclude that different models have different estimations for specific material. Also, we can understand that finding necessary parameter to obtain an estimation is important as the number of parameters does not certainly means to better modeling. Lastly, to improve modeling, there are some different optimization and curve fittings in the literature that has to be studied more deeply and different scenarios. We got help from our TAs and Alireza. Also, our supervisor and lecture coordinator helped us very much. Thanks for their help and thank you for listening.